afternoon, everyone. My name is Seong Son, and my research is about the application of brain-machine interface to exoskeletons. First, I come up with this idea of this research from a documentary I watched before. It was about the disabled people and the medical technology that helped them. In this documentary I watched, I found some paralytic patients, and then like the ones who couldn't move their body parts by their own, like quadriplegics, and they using the wearable robots to support their body movements or even start the body movements. And this kind of made me to come up with a question: how would they control the wearable robot when they couldn't even control their body parts? And after research, I found out that it was because of a BMI controlled exoskeletons. BMI controlled exoskeleton can do things that conventional robots can't. I started this research because I wanted to investigate about the strengths that BMI has and the BMI's usement of exoskeleton industries. Before going over the whole study, I want to explain the definition of the keywords of the study. The first one is BMI, the Brain Machine Interface. This is also known as brain-computer interface, and it's a device that basically converts neuronal information to command that can control the external software or hardware, such as computer or robot arms. Due to the neuroplasticity of the brain, which is literally the plasticity of the brain, that it can change by the surrounding environments. The signals from the implanted prosthesis can be processed by the brain just like the natural sensor after adaptation. The next word is powered exoskeleton. Originally, the word exoskeleton refers to the outer skeleton that support and protect the animal's body. However, the powered exoskeleton means the wearable mobile device that is powered by a system of combination of technologies that allows the limb movements for the increased strength and endurance. The BMI, the brain-machine interface, has a lot of characteristics, advantages and disadvantages. The first one is that after connecting the exoskeleton to the EEG system, electroencephalography, also known as a brainwave, the user can control the exoskeleton just by using their brain activities. So, because of this feature, the paralytic patients, like quadriplegics, can use exoskeleton like their body parts. The second one is that it needs an adaptation process to perfectly use it. So, in other words, it needs a lot of effort and practice of the user to perfectly use it as a natural sensor. And the third one is that patients need to implant a small device inside their body, like underneath the outermost layer of their brain, or like or at least between their brain and skin. So, as you can see from here, the BMI is really strong. BMI has a really strong advantages, but also it has a disadvantage that it is really complicated. So, because of this, the typical exoskeleton doesn't really use BMI as a control. Instead, they use something like surface electromyography measurements or admittance force control. They use this because they're much simpler than BMI. Because it needs to implant some devices in the body. The surface electromyography measurements is basically reading the movement of surface muscles, and the admittance force control is reading the acceleration and force of the body movements. However, these two technologies can't really solve problems of paralytic patients because it needs the body movement to start the robot's movements. So that's why that's why BMI controlled exoskeletons are here. So there are some models like Rex from Rex Bionics or Locoman from Hokuma. And they are the BMI controlled exoskeletons, and they are still in development. So in conclusion, the exoskeleton have potential to bring clinical benefits to across multiple physiological systems to users with disabilities. The application of brain-machine interface will significantly increase the scope of target of this clinical benefit. Thank you.